Picking up where the last lecture left off for Chapter 8, we were looking at lift technique. We discussed proper, improper, and then what people really do in real life is mostly freestyle. The next point of interest is how much can be lifted safely. And so companies are interested in this. They want to set, for example, if they set an administrative control that a load over such and such a weight, you need to get help or you should not lift it if it weighs so much. They want to know kind of what is that limit. And so if I were to ask you, have you experienced any weight limits at companies? Some of you might say, well, I've been at a company that's 50 pounds. Some companies have 75 pounds. Other companies have 40 pounds. And you're like, well, what is safe? If I twist it and say, what's the safe speed limit on Kentucky roads? You're probably going to say, well, it depends on the road, depends on the conditions, and so on. There's no one answer. And so similarly for lifting, there is no one answer. Companies have just, I don't want to say randomly selected a weight, but they've made a determination that they need a specific weight and they're going with it. But really, it's going to depend. And so how do you, if it varies from job to job, task to task, how do you find out what's considered a safe load for humans? In order to answer that question, we're going to be using the NIOSH lifting equation, and I'll refer you to your workbook, page 81, if you'll turn to that. We're going to be using the NIOSH lifting equation, abbreviated NLE, to try to prevent lifting-related, lowering-related, low back pain, low back injury in workplaces. Page 81 gives you the first paragraph, gives you some background information. Basically, it gives you again that 20-25%, 20% injuries, 25% of workers' comp annually. It defines a lifting task as the act of manually grasping an object of definable size and mass with two hands and vertically moving the object without mechanical assistance. And so lift is vertically moving up or down. And then the bottom part gives you a definition, the second paragraph, a definition of a recommended weight limit. Weight limit, to kind of paraphrase that, it's the weight of the load that nearly all workers, and on my slide you might want to add to your workbook, page 81, it protects at least, so greater than or equal, at least 75% of your healthy workers. So we use the NIOSH lifting equation to prevent back injuries in 75% of your healthy workers. If you have a worker with low back injury already, this equation doesn't protect them. Instead, we'd have to use another method that we talk about in the graduate level ergonomics class. But this assumes healthy workers, most are protected. We're going to use the equation in the middle of the page, and then the bottom of the page is a set of equations that really define the main equation, but we're going to use a somewhat easier method. Again, this table is reserved for the graduate class, but I provided it just in case you ever need it as you're studying, for example, for the CSP exam. If you'll turn to page 82, I'm going to ask you on page 82 to draw a couple stick figure drawings, and this will be 2 points of time in the lift. We're going to start out with the beginning of the lift. We're going to label this the origin. And so if you draw a stick figure at the origin, and if you consider it's a lift, he might be trying to lift a box from the ground. And so this will be the origin. As he puts the object down, as he puts it down onto a table, where the load ends up is going to be called the destination or the end of the lift. Okay, so we'll evaluate or analyze a lift at those 2 points in time, the origin and destination. So if you'll draw those two stick figures on page 82, we're going to look at some of the things that make a manual lift riskier. And you've probably covered these in maybe some of the lifting training you've had, but they always tell you to keep the load close, hug the load. They tell you to don't lift from the floor, don't lift overhead. So lifting from the floor is stressful on your back, lifting from overhead is stressful on your arms and shoulders. They tell you to not lift too frequently, and so we want a relatively infrequent lift. Longer work durations puts more stress on your body, so you want shorter durations. They tell you to get a good grip. They tell you not to twist. And so we're going to incorporate those things. We're going to try to measure those, define those, so that we can find out how risky a lift is. Those will be variables, so task variables that we need to measure. And you can see that I just inserted my definitions right on top of my drawings, and so I'm going to redraw down so you can see them. I'm going to redraw an origin and redraw a destination for you. So this is one single lift beginning to end. Okay, on page 82, I'm going to have you underline or highlight some things that that are important so that you can get to those very quickly. For the load constant, if you underline the whole, this is on page 82, the whole sentence, load constant is equal to the maximum recommended load weight to be lifted under ideal conditions. If you'll add in this part about equals 51 pounds, 51 pounds is our starter weight. It's the weight that NIOSH has concluded is safe for 75% of people if they do it under ideal conditions. And so companies, seeing that NIOSH recommends 51 pounds, a number of companies have gone with, well, we'll just say 50. We're just going to round it. And so their weight limit has come from this 51 pounds. The next factor I want you to take a look at and underline in your workbook, page 82, is the horizontal location. I want you to underline is the distance of the hands away from the midpoint between the ankles. So distance of the hands away from the midpoint of the ankles. Let me erase this word here so that I can do some drawing that you can copy into your workbook. And let me go ahead and change the ink color maybe so that hopefully this will stand out a little bit better. So red and green, thinking of Christmas. Okay, on your drawing, the distance between the hands and the ankles, if you'll draw from the ankles out to the hands here, if you'll draw an arrow, label this as H at the origin. Similarly at the destination, it has its own H. And so if we draw that in, oops, I should draw from there. So H. V, vertical. In your workbook, if you'll underline vertical location is the distance of the hands above the floor measured at the origin and destination. And so for V, it's the distance of the hands above the floor. And so at the origin, we have a V. At the destination, we have a V. Okay, those measurements are both in inches, and so all we need for this is a simple tape measure to measure H and V. The next variable is distance, the travel distance of the load, and it's just vertically how far the load is traveling. And so if your workbooks, if you'll underline D is equal to the absolute value of the difference between the vertical heights at the destination and origin. So the absolute value of the difference between. And so essentially D is right here. You've moved from a low hand height to a high hand height. And so D is equal to just the difference. And so the difference is the V destination minus V origin. Absolute value of that. And so if you're doing a lift, it's going to be positive. If you're doing a lower, it's going to be negative, but the absolute value will take care of the negative. And so essentially we're just subtracting those two differences to find out how far it's traveled. Your next variable is your twist, only NIOSH calls it angle of asymmetry. But you're trying to look at how much your back is twisting in degrees. And so if you'll underline in your workbook, page 82, A is equal to the angle of asymmetry, is the angular measure in degrees of how far the object is displaced from the front mid-sagittal plane of the worker's body. And so essentially, you should be facing forward. If you twist to either side, the right or the left, we want to find what is the angle of the twist. And in that case, we'll use a goniometer to try to measure that. Okay, so asymmetry is twisting. F, if you'll underline frequency of lifting, is the average number of lifts per minute tracked over a 15-minute period. So average number of lifts tracked over a 15-minute period. And so people are doing lifts maybe regularly and regularly. You watch them for 15 minutes and come up with a lifts per minute average. It might be 2 lifts per minute, it might be 5 lifts per minute, so on. And then lastly, flip over to page 83 under the coupling paragraph. Coupling, if you'll underline, refers to the quality of the hand to object coupling, handle, cutout, or grip. And so essentially this is the grip that you have on an object. They call it coupling, but it is just the grip. Okay, so these are the 6 variables that we have to measure in each lift we're going to evaluate. We want to measure with tape measure, with goniometer, with a clock. The coupling is going to be somewhat subjective, so we'll have some definitions for those. It's easiest to learn this by jumping into a problem, and so NIOSH has provided what they call a job analysis worksheet. And this is on page, I've got it labeled page 11. You'll notice in your workbooks that we've got the regular page numbers, the workbook page numbers at the bottom. Well, for this particular chapter area, I also have the pages within it labeled at the top. So they're called RWL- a page number. If you flip to page 11, you'll see a job analysis worksheet. And so this will be a clean one that you can keep to use. But we're going to start looking at a sample problem, in example 1, a package inspection task, which was on page 12, and then we'll fill in the job analysis worksheet on page 13. And so if I give you a minute to read the job description, again, this is page 92 in your workbook or page RWL 12. Okay, so from here we're going to be filling in the job analysis worksheet. And so for the top of the job analysis worksheet, this part up here, I do want you to finish that off. I do want you to do it. I always say I really don't care what you put in. I'm not checking for accuracy. I'm not checking for correctness. I'm simply checking that you did it, that you're used to keeping background information so that in 6 months you know who, what, when, where types of information as you refer back to this. And so for the department, with this package inspection, it might be in the inspection department, the shipping department, the quality control department, whatever you want to put here is fine. I'll simply label it shipping department. The job title, again, I don't know, maybe you're a quality control inspector. If you use lifter, if you use whatever you want, that's fine. Analyst name will be your name. The date will be today's date. And job description will be something along the lines of inspect and lift package. So inspect and lift package. Okay, again, I really don't care what you put up there. I just want to see that you've done that part of it, that you keep maintaining that part of it. But when we get down to step 1, this is where I'm checking for correctness. And so the first thing in this problem that you're asked to identify is the object weight. And so going back to the word problem, you see that in the picture, the box is labeled as 26 pounds. 26 pounds. I'm going to ask you to insert that as the object weight for both the average and the maximum. And so for the undergrad class, going to keep it easy. We're always lifting within a task. We're always lifting the same weight. This box is always 26 pounds. The next step is to look at the origin, and so you have to decide which of the locations, the low shelf or the high shelf, which one is the origin, which is the destination. And so as you read through, you probably realize we're inspecting it on the low shelf, and so the low shelf is the origin. We're putting it up on the high shelf, so the high shelf is the destination. And so on the step 1, we're looking at the origin, H and V. H is the distance between the ankles out to the hands. So midpoint between the ankles out to the middle knuckle of the hands. This is H at the origin. And you can see from the picture that it is 10 inches. Our V is vertically how high are the hands off the floor. And so you see as he picks up the box, as he picks it up right here, that his hands are at the top of the shelf. The top of the shelf is this is equal to V. So V is 22 inches. We then move on to the destination, find the H and V at the destination. In this case, we see that now the distance between his ankles and his hands when he puts it on the shelf is going to be 20 inches. And so that's equal to our H. So H is now 20 inches. And V, again, as he puts the load down, his fingers are touching the top of shelf 2. And we see that the top of the shelf 2, the V is equal to 59 inches. Okay. The next one's a subtraction, so calculation. The vertical distance, how far has it moved in space? We're wanting this distance right here, the distance between shelf 1 and shelf 2, and so we simply subtract V at the destination is 59. V at the origin is 22. You don't really need the absolute value for this, but if you get used to using it, you'll always be okay. And so that's equal to 37 inches. It's moved for 37 inches vertically. The next two, if we look at the origin, how much is he twisting his back? You see that he's lifting directly in front of him. He's not twisting his back, so it's 0 degrees of twist. At the destination, when he puts it down, again, it's right directly in front of him, so he's not twisting his back. Not twisting is 0 degrees of twist. The next couple we can't show on a picture. You can't show frequency on a picture, duration, so you get those from the word problem. It tells you that you're lifting at a rate of 3 lifts per minute. And duration, it gives you 45 minutes. You want to put this in hours, and so the hours will be 0.75. So 45 minutes is 0.75 hours. And then finally, the object coupling. How good of a grip can he get on the box? We have to identify it as good, fair, or poor will be our choices. And so for that, to look at coupling, I'm going to send you to page 7, RWL page 7 in your workbook. And so if you'll flip back to RWL page 7, and you underline the same things I've got underlined in the slide. Basically, good, fair, or poor. Good means that you have handles or handhold cutouts of optimal design. So you have good handles built into the box or built into the container. If you don't have that, then a second definition of good is comfortable grip, in which the hand can be easily wrapped around the object. And so you've got fingers wrapped around the object pretty solidly, pretty completely. In this case, we have a box. You can't wrap your fingers around the full box, and so it doesn't meet good. And so next we check, is this box fair? Is it fair? And well, if it has handhold cutouts of less than optimal design, so maybe they're a little bit small, maybe they're a little bit sharper, they're not perfect handles. Our box doesn't have handles, and so you look at a grip in which the hand can be flexed about 90 degrees. And so you see the edge of the box, you can flex your fingers 90 degrees around the edge of the box. And so you might want to add yourself a note, a little star down here on the fair, say a box no handles. Box no handles will be fair. And then so we'll insert fair into our job analysis worksheet. But just for completeness on this page, your poor is everything else. And so I've got containers, less than optimal design, loose parts, irregular objects that are bulky, hard to handle, have sharp edges. And so you can think of, I don't know, you move a TV, you move, I don't know, a barrel, you move something that's weirdly awkward. If it's not that, you're lifting non-rigid bags in part 2, and so bags of kitty litter, dog food, grain, seed, just non-rigid bags. Okay, so once you've got those, again, we're going to be putting fair into our object coupling, and that completes step 1. For step 2, we're going to look at, it's going to ask you to find the RWL, the recommended weight lifted for the origin. We always do the origin. We're going to do the destination if certain conditions are met. And so we'll do it if and only if. Okay. But starting with the origin, we always do the origin. It starts out with the load constant of 51 pounds. That's given. We always start with that. The second empty box, or the second box, the first which is empty, refers to the HM, the horizontal multiplier. That's at the origin. Origin H is 10 inches. And so we want to find a multiplier, an M, a horizontal multiplier that associates with 10 inches. And so at this point you're going to need again to switch to another page in your workbook, and that's RWL page 6. I've got a full set of multiplier tables. And so for each of those factors, each of those variables we looked at, it will have its own multiplier table. The multiplier table is set up. H will be the measurement in inches. HM will be a unitless number that is less than or equal to 1. The second part of this table in our measurement tables is metric. We're not going to use that, and so you can ignore the second part of the table. So focusing on the first part, we had an H of 10 inches. 10 inches. H refers to an HM value of 1.0. And so in this case, we stick a 1.0 into our box. Second variable is VM. VM at the origin. VM at the origin. V is 22 inches at the origin. So we want to find what is VM associated with 22 inches. I'm going to backtrack and go to, my tables are a little bit out of order. I expanded them, blew them up in size a little bit so you could see them a little bit better, although this one looks pretty good also. And so if we've got a V of 22 inches, you can see that again, metric, don't have to worry about. V of 22, we don't have 22 on our table. We've got 20, 25. And so I want you to guesstimate somewhere between that. If 20 is 0.93, 25 is 0.96, you might say, well, I'm going to use a 0.94. Somebody might say I'm going to use a 0.95. I would say either's okay. Either's okay, both will get you there. I happen to use a 0.94, so I'm going to stick a 0.94 in my box. Similarly, when we go to DM, we take a look at D. D's 37 inches. We go back and our distance multiplier, 37 is not on there, but 35 and 40 are. So we go midpoint between. You see our choice is between 0.87 and 0.87. So I guess we'll go with 0.87. Next variable is AM. AM is associated with an angle of 0, and so you take 0 back to your multiplier tables. 0 is table 4, or sorry, the asymmetric multiplier is table 4. For 0 degrees, our AM is 1.0. Next is FM. FM gets to be a little bit trickier because it depends on frequency rate. So frequency, we call it frequency in lifting, not repetition. So it depends on our frequency rate. It depends on our duration. And it also depends on our V at the origin. So those three things. And so going back to our frequency, I want you to write yourself a little note. Say that the V in table is V origin. Always. So we had a frequency of 3 lifts per minute. we had a duration of less than an hour. So it was 45 minutes is less than an hour. We can see these are starting to match up right here, now that I've scribbled over it. The next thing we need to decide, is it a V less than 30? So 22 was less than 30. And so we're at this value right here. For this particular combination, it doesn't matter. It's 0.88 on both cases. But on some problems that will come into play. And so we put a 0.88 here. And then lastly, we're at our coupling. Coupling is fair. So we're on our final table, table 7, fair. You see we have a choice of 0.95 and 1.0. For this table, Nash's definition changes. Right? I want you to write a note. V in this table is V origin or V destination. It depends on which you're evaluating. So it depends on which one you're evaluating. And so in this case we're looking at the origin. At the origin, our V was 22 inches, the one I've got circled here. So 22 inches is our V. 22 is at less than 30, greater than 30. We'll find it's 22 is less than 30. And so our coupling multiplier is that 0.95. Once you get those, we've got the load constant 51, multiply it by 1, multiply it by 0.94, so on and so on. Just keep multiplying these together. Plug that in your calculator. You're going to come up with an RWL. We're trying to calculate the RWL of 34.9 pounds. So 34.9 pounds. For our next class period, I would like you to do the destination. So do the destination. I said we're going to do it if and only if. Well, the if on this part I've got on this slide, if significant control occurs. In this problem, they told you there is significant control, but that basically means if the load is regrasped, momentarily held, positioned, or guided at its destination. In this case, the box has been inspected on the low box. He doesn't want to damage it as he puts it on the shelf, and so he is guiding it carefully to its destination. In that case, we do the destination, do if significant control, and here, yes, there is. So I want you to fill in each of the boxes, go and find the multiplier values, complete the RWL. So for the next class period, we'll come back and check this. And then I want you to do step 3. You insert the object weight was 26 pounds. You input the RWLs that we just calculated at the origin was 34.9. At the destination, you're going to find that. I want you to calculate, bring this to class, and we'll check the numbers. We'll check this problem on Monday and then look at finally how do we interpret what we just did.